Hi everyone, I'm Jacopo, and together with Sam, we are going to present our work on modeling short and long-term structure in symbolic music with attention and recurrence. Let's start with a quote from the great Stravinsky, highlighting the fundamental importance of structure in music. So, musical ideas are thoroughly organized in time by composers according to a well-defined structure, which is set to bring balance between chaos and order. Not too much order, otherwise the composition will be boring and excessively predictable, and not too chaotic. Indeed, the level of structure involved in music and the degree of change within and between levels, the complexity of a piece, are fundamental for its enjoyment. This interplay between structural complexity and enjoyment has been demonstrated to follow an inverted U trend, with maximal enjoyment being elicited when melodies occur in the middle of the range of melodic originality. So what does music structure look like? In Western tonal music, music structure is said to be organized hierarchically, with musical ideas introduced, varied, repeated, and contrasted at different time scales, from rhythmic cells to motifs, phrases, and sections, depending on the specific genre or musical style considered. Unfortunately, music generated by neural networks models does not fully capture the richness and the complexity of structure in real music. However, as human composers work with interrelations among local and global structures, we would like generative systems to imitate similar capabilities. To understand where this problem stems from, we need to take a step back and consider the task on which automatic composition systems are usually trained on, that is, music modeling. Music modeling is a specific instance of the sequence modeling problem, just with musical events rather than arbitrary tokens. More generally, sequence modeling refers to the general task of learning to predict the next event in a sequence, given the historical context of the previous events. By sampling from the distribution that the model has learned, we can generate continuation of the input sequences, one event at a time. A model capable of capturing the underlying distribution to which the sequential data is subject is a powerful computational tool enabling several tasks in machine learning. For instance, improving the performance of a music model would not just benefit music generation, but also impact on several tasks in music information retrieval, such as automatic music transcription and style transfer. This is analogous to the language modeling problem for the field of natural language processing. From a technical perspective, music is more complex than text, and this is why modeling music is not so trivial. Coming back to the original problem, learning musical structure at all the possible timescales, thus encoding the repetition and the variation of musical ideas, is already there with monophonic music. Modeling music becomes progressively harder on polyphonic melodies and multi-track music. This introduced the challenges of learn bidirectional dependencies across time and simultaneous notes, and three-directional dependencies across time, note simultaneities, and voice, respectively. In this work, we focus on the problem of learning musical structure, as it is one of the major open issues currently jeopardizing the application of music models for automatic composition. In fact, a model that cannot learn musical structure will not be able to generate structured music. To sum up, given a sequence of past music events, notes, temporal slices of notes, grouping of notes, depending on the granularity of the chosen representation, our music model needs to predict or generate the next music event in the sequence. Considering the nature of the problem, our model can be either Markov model. However, they will require an explosive number of states to repeat arbitrary patterns. Or maybe a recurrent neural network, such as an LSTM. Although recurrent networks have been extensively used in music modeling, they struggle to learn long-term dependencies, meaning that their generation tend to be either too repetitive or too contrasting after a while. And what about transformer? Well, they are currently the state-of-the-art in music modeling, but they still suffer from several problems. In particular, they struggle to learn local structure, and they do not possess an inductive bias, that is a tendency to learn iterative or recursive transformation, which instead recurrent networks do. Transformers also have resolution problems and complexity issues with long sequences. To the best of our knowledge, Two approaches are mostly used to improve a model's ability to learn musical structure. Conditioning on structural cues, such as the music events at potential structural boundaries, and increasing the complexity of a model by stacking additional recurrent layers or increasing the number of memory cells. Instead of considering recurrent networks and transformers as two contenders in the music modeling game, our approach is based on the hypothesis that self-attention, the strength of transformers, is crucial for learning long-term structures. Recurrence addresses several limitations of transformer, such as learning local structures, and inductive biases facilitate the integration of both these modeling paradigms whilst optimizing the use of parameters. Our architecture incorporates all these mechanisms and provides self-attention at a linear cost, which allows processing entire musical pieces, a crucial requirement for learning music structure at all the possible timescales. Sam will now explain our architecture in more detail.
Hi, so to describe our architecture in detail, I'll do this step by step by addressing each of the problems that Jacopo has discussed already. So to start with, there are two neural network architecture types, recurrent neural networks and transformers that form parts of our model. So RNNs are already widely used, both for natural language and music, but as mentioned, they have problems learning very long-term dependencies. So instead, we'll begin our discussion of the architecture by looking at the transformer, which lies at the heart of our architecture. So these were introduced in 2018 and have quickly become incredibly popular in natural language processing and are gradually replacing recurrent models in many contexts. So for example, the GPT models are transformer-based, but there has been some success in applying these to music generation as well. So instead of processing a sequence node by node like an RNN would, transformers share information by looking at pairs of nodes. So this is called the softmax attention mechanism. So each node, it has learned how much a node cares about other nodes in the sequence, and propagating information across a sequence only takes one step to do, no matter how far away the two nodes are. Whereas with a recurrent neural network, to propagate information, it's got to travel back all the way through the sequence. So as a result, this means transformers have a capacity to learn much longer range connections. However, unfortunately, the computational complexity of performing this operation for the vanilla transformer is quadratic in the sequence length, which is prohibitive for the kind of length sequences we want to consider. So to solve the complexity issues, very recent developments in transformer architectures have introduced a new kind of attention, which is in fact linear in the sequence length. So this is really good news because it means we can throw really long sequences at a transformer model and it can cope with them without requiring a supercomputer to do so. So on a high level, this is done by defining the attention between each pair of nodes as a kind of multiplication, a kind of dot product between vectors. And this allows a neat factorization, which allows reuse of computation between all of the sequence positions. So the details of how this is done is in the appendix of our paper. So the next problem to solve is the inductive bias problem. So to do this, we incorporated aspects of a kind of transformer called the universal transformer. So this differs from how you normally use transformers in that instead of having a stack of transformer layers as you normally do, you have a single transformer layer which has a recurrent connection to itself. So this is a recurrence in depth, not a recurrence in time. So in effect, this is just a weight sharing across a stack of transformer layers. However, the original universal transformer paper used softmax attention, whereas ours uses the linear attention mentioned before. So combining these two isn't a problem. So finally, to solve the resolution issues with transformers, we introduced some recurrent neural networks to the mix. So the resolution issues are caused by the explicit positional encoding in a transformer. So without a positional encoding, the transformer has no notion of time. It's basically operating on an unordered set of data unless you tell it when each part of the sequence occurs. So by adding an LSTM to the input, this removes the need for an explicit positional encoding in favor of a learned positional encoding. And it also has other benefits like helping to locally contextualize the music. For example, learning a representation of what chords are active, what notes are currently pressed. And we also added an LSTM to the output side of the architecture as well. So this helps reconstruct this data because it might be difficult to do so locally. So for example, if the model decides to press to begin a note, it needs to remember to unpress that note after a specific amount of time. And this is something that requires local knowledge as opposed to global structural knowledge. So intuitively, if this was a natural language model instead of a music model, this would be equivalent to remembering to close your brackets and that kind of thing. And LSTMs, we know, are pretty good at learning precise timings as well, whereas transformers aren't quite so good. So we've now arrived at our full architecture.
Based on our hypothesis, we evaluated our method on the music modeling task and compare its performance to a vanilla LSTM, an attention LSTM, a transformer, and a universal transformer. To train and evaluate our model, we chose a dataset of long and structurally complex musical pieces, the Maestro collection. The dataset collects more than 1,000 classical piano performances in MIDI format, which we quantize to the 16th note and transpose to all keys to learn transposition invariant features. To circumvent the problem of learning note simultaneities, chords are unrolled in time and so represented as arpeggios. We do not trim nor discard our music sequences, as we want to study our models on entire music pieces, thereby testing their ability to learn structural properties of music. Models are evaluated on the test set based on the cross-entropy laws, measuring the distance between the target distribution, the actual music sequences, and the predicted one. In line with our hypothesis, we found that the use of attention improved the modeling performance of the vanilla LSTM, although the transformer-based networks are still better at predicting music. The small improvements of the transformer over the universal transformer is not statistically significant, meaning that universal transformers can achieve the same performance with half the parameters. Finally, the LSTUT achieved the best performance on the Maestro dataset. To analyze the ability of the LSTUT to learn music structure features, we inspected the attention distribution of the attention heads and compared them to the self-similarity matrices computed on the same music. Self-similarity matrices are extensively used in music structure analysis. To compute one of them, all elements of a music sequence are compared with each other for similarity. When visualizing such matrices, repetitions typically yield path-like structures, whereas homogeneous regions yield block-like structures. As an example, we chose Fly, a minimalist composition for piano, exhibiting both local and global structures. This is particularly evident after inspecting the piano roll reported above, as well as from its self-similarity matrix below. As you can see, the attention distribution of this selected attention head on Fly is not so different from the self-similarity matrix, especially if we note the block-like structures of different size emerging from both this visualization. This observation supports the fact that the LSTUT can learn structural features at different temporal resolution, even if the model has never seen a minimalist piece in the training set. So the takeaway message of our presentation is that you should use a universal transformer, if possible. Consider entire tracks to learn musical structure at all possible time scales, and combine self-attention with recurrence to take the best of both worlds. It is now time to start generating some structured music with our model. And to provide a more comprehensive study to the field, we are now conducting an extending experiment to compare multiple architecture for music modeling and different representation of symbolic music to analyze their impact on learning structural features at different time scales and on different datasets. Another promising direction that we are investigating is the alignment of attention heads with self-similarity matrices for promoting their specialization, structurally speaking, and increasing the interpretability of our models. Thank you for your attention and stay tuned for future developments.